This video is about slopes and specifically about the relationship between position, velocity, and acceleration. Position represents distance away from starting point. We usually measure that in meters and use the symbol x. Velocity is the rate of change of position. Change in position, meters over change in time, meters per second. Velocity is representing a distance over a time, a change in position as time passes. Acceleration, likewise, is a change in velocity. Velocity, meters per second, changing per time per second, meters per second, or as it's commonly said, meters per second squared. Correspondingly, if we graph the position x as the vertical axis as a function of time, the horizontal axis, then the slope of that graph will be a change in position relative to the horizontal change, the rise over the run. The rise will be a change in position over the run, the change in time, a distance per time. The slope of the position graph is the velocity. Likewise, the slope of the velocity graph is the acceleration. Velocity, vertical axis, meters per second, rise over run, time in seconds, rise over run. The slope of the velocity graph is meters per second, a change in velocity as time passes. In other words, an acceleration, usually represented in units of meters per second squared. Let's go through the animation here and see if we can make sense of the events that are happening. Let's start back at the beginning and look at segment A, first examining the position versus time plot. In the position versus time plot, at time 0, the value of the position starts off at the green dot at a location which is labeled as 1 meter. As time ticks forward, the object is moving forward, and at the end of segment A, its position has gone from location 1 to location 3. It's gone forward 2 meters in a time of 1 second. So correspondingly, the velocity for that segment was 2 meters per second. If we look at the velocity graph, we see that the value of the velocity was indeed 2 meters per second, and it stayed fixed for that full interval. The value was constant in segment A. The value of the velocity was constant because the slope of the position curve was not changing. We were moving forward at a constant speed. Now in segment B, something a little different is happening. Let's look back at the position plot. We're moving from position 3 to position 4, but the slope is going from 2 meters per second to a value of 0, a horizontal slope at the end. So in segment B, we were actually slowing down. We went from a velocity of 2 meters per second to a velocity of 0. Correspondingly, in the velocity graph, the value of the velocity dropped from 2 to 0. In segment C, looking back at the position graph, we actually start moving backwards. We're moving backwards with our foot on the gas pedal in segment C. We start off with a slope of 0, not going anywhere. We're momentarily at rest. And then we move backwards in segment C, a total distance backward 1 meter in a total time of 1 second. So the average velocity was -1 meter in 1 second, -1 meter per second. It must be that our final velocity was -2 meters per second, because the midpoint, the average between 0 and a slope of -2 is -1. The average velocity in segment C was 1 meter backward in 1 second of time. Correspondingly, the velocity graph went during segment C from a value of 0 to a value of -2. In segment D, we're still moving backwards, looking at the position graph. We're still moving backward 1 meter as we move 1 second in time. However, we're coasting to 0 in segment D. In segment D, we're moving backwards, but with our foot on the brakes. At the end of segment D, we're back to position 2, and we just stay fixed at position 2 for all of segment E. So segment D is with the parking brake on. Going back through everything, in segment A, we're moving forward at a constant speed a constant slope, the velocity remains fixed at 2 meters per second. In segment B, we're still moving forward, but we're slowing down. The velocity is dropping from 2 to 0 in meter per second units. In segment C, we start going backwards. The value of the velocity, the slope of the position curve, starts to tend negative, and we see the velocity line go from 0 to -2 meters per second. In segment D, we're still moving backwards, but we've got the brakes on. We started off with a negative slope, and that slope tends down to 0 at the end of segment D. In segment E, we maintain the 0 velocity. We maintain a position of 2, and the velocity is constant with the value of 0 all through segment D. Let's look closely now at the relationship between the velocity curve and the acceleration curve. Just like the value of the velocity was the slope of the position, the value of the acceleration is the slope of the velocity. Let's go back to the beginning and look at the middle plot, the velocity plot. The slope is now given by the red line. The slope is fixed at 0. Then the slope goes negative, -2 meters per second in a time of 1 second. Indeed, the value of the acceleration drops to -2. And it maintains that value all through segments B and C. Segment D, the slope of the velocity curve has turned positive. The acceleration value has jumped up to +2 meters per second squared. In segment E, the slope of the velocity curve is going to 0. Likewise, the value of the acceleration goes to 0. Let's look back one more time at the whole process. Moving forward at a steady rate, then forward with the brakes on, then backward, speeding up, then backward with the brakes on, and then sitting still in the last segment. One thing to note, and a common misconception, students sometimes think that positive acceleration means speeding up and negative acceleration means slowing down. That's not correct. In segment B and C, both, we had a negative acceleration. A negative acceleration simply means that the velocity is becoming more and more negative as a value. If you're moving forward, as you were in segment B, a positive value of the velocity, forward motion with a negative acceleration means slowing down. In segment C, we're moving backward, a negative value of the velocity. Backward motion with backward acceleration means speeding up. If you're doing more of the thing you're already doing, you're speeding up. So the correct way to say it is, if the velocity and the acceleration have the same sign, then you're speeding up. If they're opposing each other, then you're slowing down.